So we're changing gears today, like I said last time. We're going to talk about reflection, which is different than what we've been doing. We've been doing object-oriented based metaprogramming. This is more pure metaprogramming. So this is reflection. So a lot of people think that programming is kind of like this. You write the program, and then the program gets executed in some sort of runtime, right? You know, we define what variables we want, and then those variables like exist somewhere. And then we get some output that we like or we don't like. But we think of it in these three distinct phases. But you can actually break this down a little bit. You can actually get information back from the runtime in your code. And so you can almost visualize a bit of a mirror right here at the runtime. That's what we're reflecting. We've got the program and we've got the runtime, but what our program is going to do is actually look explicitly at the runtime, get information about it, and then we're even going to change it. So the official definition of programming reflection is the ability of a program to view and modify its own structure at runtime. So that's reflection. And as we go through reflection, something to keep in mind is that usually in Python at least, this isn't always the case, but in Python, if you think something might be reflectable, it probably is. And there's probably a function built in to do that. So can anyone think of some reflection that we've already done? We've got this type function here, and right now we're using it as a constructor. We're making a new type. But before, we were using type like this. Type, and then we're passing in some sort of variable, and this will return the type of that variable. That's reflection. Because what if instead of passing 1 here, we passed in some variable, some parameter, something that we don't know about, and we call type on it? What the type function is doing is saying, okay, let me look at the runtime and see what this variable actually is. And I'll tell it to you, it's an int. So that's actually reflection. We're looking at the program itself at runtime. So the way I want to go through reflection is kind of goal-oriented. I've written the program, and this is on GitHub, on the GitHub. So you can read it if you want. You can pull it up now if you want. But basically, what I've written is a debugger. That's kind of a common theme. Debugging is a classic metaprogramming goal because it is a metaprogram. Any sort of debugging program you use is a program that's explicitly modifying and working on programs. So this is a debugger I've written, and you can see when the debugger is running, we call this foo function, and then immediately we get the source code for foo printed out right there. And we get a little tick mark on the line that we're on. Kind of helpful, right? We get a list of all the global variables, we get a list of all the local variables, and then we get to see the call stack so far. We've got a module and a foo. It turns out that whenever you're calling a function in Python, the highest level on the call stack is always the module. So just keep that in mind. Even though we're only calling one function, there's 2 things on the call stack. That'll come back. But then check this out. This is really cool. While the debugger is running, we have the opportunity to set a variable. So we're on this line here. We're on C equals A plus B. This line has not yet evaluated. Okay? And the debugger is going to prompt you, would you like to make a change to the program runtime right now? And I'm saying, yes, I would. Set A to be A plus B. And now look, we're on the next line now. Print C. What is A? A was 1. Now A is 3. Right? We didn't set A, we set C. C got set. But in between these 2 lines, we also said, go ahead and set A to be A plus B. A plus B is 3, now A is 3. And look, not only that, but C, instead of being 3, is 5. Because C is A plus B, B is 2, A is now 3, and 2 plus 3 is 5. So we've modified the runtime at runtime. Okay? And we see locals, call stack. This time we don't set any variables. The function returns and we get 5. So this is the debugger that I've written. And I'm going to go through the process of how you might write something like this yourself. So the first trick is we want our debugger to run in between lines, right? That's kind of tricky. But it turns out with just a little bit of Googling, there's a function for it. Like I said, if you think it's possible, it probably is. In Python, you can import system first. Import system, sys, and then you just call it sys.setTrace func. And whatever you pass in as func there is going to be called every time you call a new function. So you might have seen when you're trying to debug like error messages in Python or Java or whatever, it'll say like trace back, error on line blank of blank, on line blank of blank, on line blank of blank, trace back. Right now we're setting the trace. So like every single time a new function is called, the tracer will be called. So we're going to pass in a func, and that's how we're going to hook into Python between the lines. So we're writing between the lines. That's cool. Okay, takes in a func, and that func must take in a frame, event, and an arg. That's just what sys.setTrace expects. Sys.setTrace expects a function that takes in 3 parameters, frame, event, and arg. And this function, func, can optionally return another function, and that function will be called between lines. So this first func, the func that we pass into setTrace, is called every time we go a level deeper on the call stack. So every time we call a function, this func will be called. Every time we go to another line, this func will be called. So here we can tap into 2 levels of Python. We can tap into the method calling level and onto the line by line level of Python. So let's just try this out, right? I've got a function printer. It takes in any positional arguments. We're going to print out those arguments and then return printer. This is going to allow us to both look at functions when they're called and lines when they're called. So, do you see the interesting recursion here? It's just so cool. First-class functions never get old. We've got a function that isn't calling itself; it's returning itself. And that's technically recursion, I think. I don't know what the technical definition of recursion. But okay, we import sys and we set the trace to printer, just so we can see what this frame, event, and arg is. So we set the trace, and then let's just call printer, just so we call something and trigger some trace calls. So we call printer, and right away we get frame object call none. We get frame object line, frame object call, frame object line. This is the output of the printer. The printer prints out the tuple of all the arguments that were passed in, and we passed in test. So it's not clear at this point what these frames are. You don't have to worry about it yet. But basically, some stuff happened, and eventually our printer was able to print. And so we got test just like we wanted. And now we get some more frame objects. And then this is the result of calling printer, because remember, printer returns printer. So here's the printer that was returned. And then another frame object. This one says return. That's kind of interesting. So again, you don't have to worry about what these frame objects are and what's actually happening here. The important thing is that we've tapped into some serious, like, low-level stuff, right? We've got code running between lines. So that's the frame, that's the event, that's the arg. And you can kind of see, like, in order to call print, we have to call. We get a call event. Then we get a line event. A line executes, and that line makes a call event. So you can see how kind of like the code is kind of producing some output here that kind of makes sense. So let's start working on our goal. First, let's try to get access to the global and local variables in the function that we're executing, right? So it turns out that Python has built-in methods, global methods, called globals and locals. Who's heard of globals and locals? Okay, a couple people. These are reflective functions. What they do is they return all the global variables and all the local variables at that point in the runtime. So, like, let's say we're just writing, like, in the global scope, some script, and we say, like, A equals 1, B equals 2, and we call globals. We'd see a dictionary mapping A to 1 and B to 2. And it also, if we're in the global scope, locals will also point to that same thing, because when you're in the global scope, globals and locals are the same. It's not until we get into an inner scope, a function or a class or something, that locals takes on different meaning. So let's try using those to print out globals and locals. We've got a, I kind of shouldn't have named the function that. This is naive. We take in a frame, an event, and an arg. We're going to print globals and locals, and hopefully that'll show us what the global and local variables are, and we'll be halfway done with our debugger, right? We set this as the trace, print out hello. All right, and what did we get? So this look familiar? Anybody seen a dictionary like this before? If you've ever tried, yeah. This is all the global variables. So like here you can say, when you're writing a Python program, and who's said if name equals main, right? Who's said if name equals main? That's name. Name is a global variable, and here it is. Name is main. Cool. We've got some documentation, some package. These are global variables that are always present in Python. We've got the module of built-ins. Built-in methods are always globally present. But then we've got some other methods here, like printer. Earlier we defined printer. Well, printer is now a global function, and so here it is. There's some functions that I actually define later. But like here's naive with a typo. It's a global variable. We defined it globally. Here it is, global variable, naive. And those are the local variables, arg, event, frame. Is this what we wanted? It's not quite. We did get globals. These are the global variables. But what local variables did we get here? We got arg, event, frame. We got the local variables of our traceback function. That's not what we wanted. We wanted the local variables in the function that we're debugging. We want to see the printer's locals variables, right? Because that's what we're trying to debug. We're not debugging that. This is our debugger. We want it to print out its local variables. So we're not quite there yet. And actually, you might have been able to anticipate that just based on the fact that we're taking in frame, event, and args and not using them at all. So it kind of makes sense. When you call locals, you get the local variables at that point. And at that point, the local variables are frame, event, and arg, not the local variables of printer. So we're going to have to investigate frame. And it occurred to me this morning, I added this slide, because not everybody has taken 2150, and so not everybody knows about stack frames and has done all of that assembly stuff. A frame is how the computer keeps track of what functions you've called up to that point. So it turns out that every time you call a function, the way the computer deals with that is it pushes a frame onto the call stack. Okay, and that's why when you get an error in Java, you'll see the call stack. It'll say call stack and give you all the methods that were called up to that point. And then the frame is just what you're pushing onto the stack. It contains information about the function that's being called. So let's investigate frame a little. We've got a function, inspect frame. It takes in frame, event, arg. We're just going to print dir frame. Does anybody know what the dir function does by any chance? Basically. You might remember on the very first day of lecture, I showed you the dunder dict attribute, which gives you the dictionary of all of the things that you can call on a method or all the things you can call on a data structure. Dir is just a function that gets the dict, but it does some extra stuff, and so you can basically think of calling dir on a thing as finding out what that thing can do. So what we're saying here is print out to me what frame can do. What are the attributes of frame? Can we call append on it? What can we do with frame? Side note, dir is reflection. We're passing in some variable, and we're asking dir to look into the runtime and see what's available for that parameter at runtime. So that's reflection. And let's see what happens. We're going to set the trace to inspect frame. We're going to call. And what do we get? These are all the things that we can call on a frame object. So there's some things that are built in, like equals. All objects have an equals method, frame included. But there's some interesting ones here, like clear, fback, fbuilt-ins, fcode, fglobals, flocals. Now we're getting somewhere. So let's print out globals and locals. We're going to print f.fglobals, f.flocals. Okay, so we're going to set that as the trace call printer. The global variables are the same global variables we saw before, right? The locals are the same as the globals. Because remember, the very highest level of the call stack is the module. And so that's what we're seeing here, is on the module level, the globals are the locals. But as we go one step deeper, the globals stay the same, but now the locals is args and then the tuple hello. This is good. Because before, when we printed out locals, we got the local variables of our traceback function. We would have gotten F, E, and A. That's not the locals we want. We want the locals of printer. And here we got it. Printer was a function that took in star args. Here it is. That's star args. That's what we're about to print. And then it got printed. So we've now tapped into the local and global variables of a function that wasn't our own. So we've got a traceback function that's taking in a frame, and that traceback function is asking the frame, hey, what are your global and local variables at this point? And now we're printing them out. So that part's done. We have the information to do this now. I've formatted it a little nicer, but we're done. We've gotten the global and local variables of this function foo externally with reflection. Let's look into fcode. The frame object also had an attribute called fcode. Seems kind of interesting, right? Maybe that'll give us the source code. Because if you'll note, like the very first thing our debugger does is it prints out the source code. So maybe that's how we have access to that. So we're going to print out frame.fcode. And what do we get? We get some code objects. Not super useful, because we don't really know what a code object is. At this point, you'd have two options, right? You could look up Python code object. This is where you start getting into trouble. In any other programming task, you can usually Google the answer, right? You can usually be like, Python, how do you print out a dictionary, whatever. At this point, when you're doing metaprogramming like this, it becomes really difficult to Google things. Because if you were to Google Python code object, I guarantee you will not get information about this code object, because Python noobs will Google similar things like code Python object. And they mean, like, how do you just make an object in Python, right? We mean, like, no, literally, what is a code object? Like, what does it mean to be a code object? So we've gone so meta now that Google ceases to be useful. And that's why I wanted to show you the dir function. Because dir is a lifesaver. Sometimes you cannot find documentation on the thing you're trying to call. So dir is amazing. Dir will just print out, okay, what can you call? It's like a self-documenting function. It's amazing. So these are the things that we can access on code. We can access the number of arguments that was passed in. It's kind of interesting. We can get the file name that the code was defined in. Remember cellvars and freevars from closures? We can get the cellvars and the freevars at any given point in time with the code object. We've got a co first line number. This will be useful when we're figuring out where to put the caret on the code. We've also got this co-code. So now what we've got a frame that has an fcode object, and that fcode object now has a co-code object. So let's go deeper. What's in that co-code? That's co-code. That is the compiled Python program. So I've never tried it, but I can imagine you could do some pretty crazy stuff by looking at co-code and changing the compiled Python program at runtime. I've never tried it. It probably is not supported. It's probably undefined behavior, but either way, it's not very useful for our debugger. I mean, has science gone too far? I don't know. So let's go back. Let's backtrack. Co-code wasn't useful. So what do we want to do now? We've got the globals and locals. Let's try printing out the source code and putting the little caret there, right? At this point, we need the help of the inspect module. So inspect module is now fair game. We need the inspect module. It's built in. You don't have to pip install anything. But first, I just want to note, some of this stuff gets really weird in the shell. So a lot of this stuff you actually need to test with Python files. So let's say we've got like a Python file. We're defining some foo function, and it's going to print out the sum of A and B. That's the same foo function I was showing with the debugger originally. And then we've got a bar function that's slightly more complicated. It'll iterate over some combinations, print them out. And then it's also going to be useful to have a function defined here called nop. It's going to take in frame event nargs and return nothing. So these functions are all now defined, including nop. And we're also going to define this function, which is the partial application of setTrace to nop. So now if we call end, it's going to set the trace back to nop. So we now have a way to turn off the debugger. Before, I was just setting the trace. And you'll note that if you try doing this stuff on your own in the Python shell, you'll be getting a ton of extra output that you don't actually want. And you can't actually turn off the Python shell without turning off the debugger, because it'll say like cannot inspect like the exit code. So you need to be able to turn off the debugger. This is how we do it. We set the set trace to nop. Okay? So now let's look at inspect. We've got this function called getSourceLines. It sounds promising. We're going to set the trace to a lambda expression taking in frame event nargs. We're going to print out the inspect.getSourceLines on the F code. We get an error. That's because, remember I said the very first call level is the module. Before foo is called, it actually calls the module, and you can't look at the source code for the module. So that's why that doesn't work. So instead, what we're going to do is we're going to just define a function, a helper function, that will try getting the source code lines, but we'll accept an operating system error and just return nothing instead. Now, if we set the trace to printing out the source lines with the try except, first we get none, because remember, we can't get the source lines for the module. But next, look at this. What? How meta is that? We've just called a function, getSource, on a frame, and it gave us the source code for that frame. Pretty cool. That's all we need to complete the code part of the debugger. Now if we go back to the debugger, look, I mean, the output was exactly the same. This is exactly the same as that. You just print it out. And then the way you add the caret is you just check if the current line number is equal to the... You just put a little caret on the element in the array that corresponds to the current line number. You can see that code on GitHub. So let's try doing this now, the call stack. We print out the call stack. Sometimes that's really useful, especially if you have like infinite recursion, something like that. Turns out there's a function for it. Get outer frames. You see a pattern? There's a function for everything. Now if we set that as the trace to printing out the outer frames, and we call foo, first we get frame information about the module level, and then we go one call deeper, we get frame information about the module and frame information about the foo method. And see, we actually get the very first line of the foo method too. How helpful. So, and that's in one array. So now at any given point in time, we can print out the call stack just by getting get outer frames. Okay? Now I've saved the best for last. How the heck are we going to do this? How are we going to change variables at runtime in a function that isn't even our own? I mean, we can change variables in our own function easily. We just set them, right? If we're writing the function and you want to change a variable, you just say variable equals x and it changes. But how do you change the variables in another function? Well, we need to talk about exec and eval. These are built-in functions. Exec takes in a string or a code object and it executes it. So let's exec print 1 plus 2. We get 3. If we compile some input and then we input print 2 plus 3, we get a code object. And then if we exec that code, we get 5. So does everybody see, like, you can either exec just straight up strings, or you can exec a compiled code object, and you can compile code by calling compile. Okay? And then eval is almost exactly the same thing, but instead of executing the code, it just evaluates the expression. So here, before we were executing print 1 plus 2. Now we're evaluating 1 plus 2 and printing it. You see the different order? Evaluates the expression, and we're printing the result of evaluating it. And we get almost exactly the same thing. Okay. You can pass in, optionally, to exec and eval, global and local variables that you want that code to be executed or evaluated with respect to. So let's try that. If we just evaluate a plus b, we get an error. A and b aren't defined. But we can evaluate a plus b, and we pass a as a global. We can pass b in as a local. Now if we try evaluating a plus b, we get 3. If you set built-ins to none, that'll also restrict your ability to import things like OS, that kind of thing. Now let's try executing a equals 5 with respect to these globals. All right, we've got some global variables here. Let's execute a equals 5 in this global namespace. What do we expect? Well, when we print out G now, a is defined in G. Basically, by defining these dictionaries, globals, locals, we're defining the state of some Python program. And then we're saying, evaluate this line of Python in this state and show us the changes right here. Now, an important note, and I'll get more on this on the next slide, modifying locals this way is not supported. So here's an example. If we have a function test, and the test executes a equals 5 in the current namespace, you might expect locals now, or globals, either one, but you probably expect locals to have an A in it, right? Well, it doesn't. So modifying locals this way is unsupported behavior. Sometimes it works, sometimes it doesn't. That being said, we're going to do it anyway, because you can sometimes find situations where it does work, and when it works, you can do some cool stuff. So remember, we're trying to set a local variable here by executing this plain text string that I've inputted. And to do that, I'm going to define this function setVars. This is just a helper function. It's going to take in a string, some locals, and some globals. We're going to split the string by the equal sign. We're going to strip away the white space. If the length of the array is 2, then that means I passed in 2 things on either side of an equal sign. So I must want to do some sort of definition. So what we're going to do is we're going to get the value of the right side of the expression, r sub 1. And we're evaluating it in the global and local namespace. That's why I was able to say A equals A plus B. It knew what A and B were on the right side of that expression because I'm passing in globals and locals here. And we're going to pass in the frames, globals, and locals. That's the trick. So we're going to get the value, and then if the thing that we're trying to assign is in locals, set locals at that thing to that value. Otherwise, set globals at that thing to that value. Now we're done. That's the reflective debugger. You can check it out in the GitHub. I called the file reflective debugger. It's super cool. And you can do it. That's it runs. So conclusion is Python is crazy. It'll let you do anything. If you want to know like whether a certain function was called within the last 5 minutes and who called it and what was passed in, you can probably do it. Python will probably let you figure that out. So it's worth digging around, especially with dir. Like I said, a lot of these things are hard to look up, but dir is your saving grace. And check out the inspection module. Yeah, that's it.